Okay, this is what we were learning. In last lesson in 5.7, we did derivatives of inverse trig functions. And now we're going the other way. So we're doing integrals and recognizing their derivatives so that we can anti-derive back to those inverse trig functions. Okay, so I mentioned the two you really need to recognize are the inverse sine and inverse tangent. Those are the ones that are tested on the AP exam. And the method we kind of use, it's a little bit of U substitution, but I kind of called it like U and A substitution, if you will. You kind of just have to like identify one of these patterns. And then from there, you pretty much just kind of do a little substitution to manipulate it to make it look like one of these, and then we can recognize the antiderivatives and just reback substitute in. So this one we did was a inverse sine. So with the inverse sine, we look for the radical in the bottom, and we look for some constant being squared and then the variable being squared. Then we did an inverse tangent. Tangent's easy to identify because you do not have any radicals, and you just have two things that are being squared in the denominator, even if that number is not a perfect square. Again, we can manipulate it to be so. And then we left off on this one. So basically, like our third pattern here is when you have a radical in the denominator, and you kind of see this setup where you're like, okay, well, I don't have a squared minus u squared. U is kind of like your variable of integration. Okay, so here I see I have my x squared first, and I see I have another variable of integration out in front of my radical. So that looks more like this pattern. So this one we can actually manipulate and anti-derive to inverse secant. Okay, so that's kind of like the difference between sine. You won't see another variable out in front here. You should just see like something squared minus x squared. But if you see two different variables, this would be secant. Now let me show you why. You might be tempted. You're like, why couldn't we just do regular u sub here? Because I see 4x squared. Don't write this down. But I see 4x squared, and I'm like, and I know the derivative of x squared is x. Now in this case, obviously, this would be like 16x. But you don't have just x. You have 1 over x. Okay, so here, the derivative, if you're like, oh, I just want to try regular u sub and let u be my inside, its derivative is not located within the integrand, okay? The derivative is 1 over x, so we couldn't just do a regular u sub for that. All right, so basically you'd have to recognize this pattern, and you're like, okay, how could I rewrite this as squares? So kind of like the first step I do is I rewrite them as squares. So for example, 4x squared is 2x squared, because this helps you identify like what your u and what your a are. And 9 is 3 squared. So I'm like, okay, this kind of helps me see my pattern. Let's see what color scheme I was using here. So a is your constant. A is 3. You're looking at this setup, minus a squared. And u would be 2x. Okay, so just like the normal u sub, you got to do du in terms of x, and we also have to sub in like for the dx, get our differentials in the same context of our variable of integration. So here I'd want to still do this. Du dx is 2. So solving this for dx, I get 1/2 du is the same as dx. Okay, so let's substitute in what we have here. So just like before, I'm going to bring that 1/2 constant on front, just like I normally do with u sub. Here's what I know. So I have 2x underneath my radical, which is u squared minus 3, which is a squared. And I'm replacing 1/2 du with dx. So here's the 1/2, so I'm going to replace that with. Now, I still have this x out here, okay? I don't want to leave it as just x, because then I have my integrand in terms of u's and x's. All right, so we're going to use our little equation right here. For our original substitution, we said u is the same as 2x, so we're going to solve this for x. So x is the same as 1/2 u. X is the same as 1/2 u. And again, I didn't change like what I'm substituting or anything. I just rearranged that little equation. And what ends up happening here, these would cancel. And now you can see that pattern pretty clearly. U square root u squared minus a squared. And I think I said this last time, the tricky thing, I guess, with these is that it just takes pattern recognition. Like, you might try regular u sub first if you were taking this on the AP exam and you kind of like forgot, oh, it's been a while since we've done those inverse trig, You might try regular u sub and you're like, this isn't getting me anywhere, and then you need to recognize the pattern. Okay. Same with like this one. Or when I try regular u sub, you're like, sometimes we let u be our denominator, but then I take the derivative. I don't need that. And you're like, I have nothing to replace that with. I can't have another x in here. So then that would trigger you to be like, okay, is this a special pattern I have to recognize? Now that we have it perfectly to match, we can do the antiderivative, which is 1/a inverse secant of the absolute value of u over a. I like to kind of put that all in the argument. Plus c, since this is an indefinite integral. And then we just read back, substitute in u and a. So 1/a was 3, so it ends up being 1/3 inverse secant of the absolute value of 2x. Keep that in absolute value bar. That's a linear function, so it could come out negative. Over a over 3. Can't divide those. I can't write that as 2/3 in the absolute value. One stuck in the absolute value. I would say like stuck in the bar, stuck in jail. The other one's not, so we just leave our answer like this. I just want to make sure that's right. Yes, I did that. Okay, so there's one of each. Inverse sine, inverse tangent, and inverse secant. Now again, the reason why we don't need to know the other three, we don't need to know inverse cosine, cotangent, or cosecant, is because what we know about their derivatives, I wonder if I have it here for a visual for you. Nope, these are all integrals. What we know about their derivatives is that they're very similar to sine, tangent, and secant, but it just differs by like having a -1 in the numerator, if you remember that. And that we can easily manipulate by just bringing out any number that's in the numerator and then do the same pattern. So, okay, I did record this, Jason, so I'm going to stop that right now. How's your English test?
Great.